So everybody in the universe can watch these on YouTube. Nothing's due today. We're going to finish up Flash. Homework 4 is due, and that's mostly on semiconductor physics, those slides right there. The homework associated with these slides is more homework 5, and we'll get to those slides today that are important. On Thursday, pre-lecture 18.1 is due along with homework 4. We'll talk about MRAM. Tuesday, ReRAM, and then Thursday, Dr. Cambeau will come in and talk about MRAM and ReRAM. And then our last topic will be CMOS imagers, aka Julie's life story. And then we'll have an optional final exam. Project 5. Project 3 was to build the sense amp and put it in the schematic correctly. Project 4 is to get it simulated, and then there's another schematic you have to draw so that you don't completely lose all the points. And then Project 5 has nothing to do with mentor graphics. So that will be a slight break from that. Again, I will regrade your Project 3s for everyone until Project 4 is due. Your overseas, I may bend the rules a little bit and grade your things early and grade your things later. Let's see. We're into chapter 7 now of the Comparto book, and I believe the whole thing is of the Micheloni book. I believe that whole book is posted on PBLearn. It's so we're going to talk about the read operation in more details, how you program, how you erase, how you program multi-level cells, error correcting codes, and charge trap memories, and then we'll move on into memories that are actually being commercially available now. So remember these NAND strings. What I do is I program all the cells to have either a low threshold voltage, which is their default, or have a higher threshold voltage by injecting charge into the floating gate. I turn on all the other transistors with a very high voltage that is enough to turn on both the zeros and the ones. And then one row that I'm selecting to read, I'm going to put at B read, so that if this one is, if I have a 1 programmed in there, it's above the threshold voltage, the transistor will turn on and current will flow. If there's a 0 programmed into that particular cell, then no charge moves, there's no current, and that is defined as a 0. And we'll talk about the readout and the sense amp for a NAND flash later on in this lecture. And then we'll be done. And we'll just talk about, basically with MRAM and ReRAM, we're going to talk about the physics of the devices themselves and not the electronics around them as much. Okay, so 2 different things I want to do here. If I want to erase, basically what this whole table says is that VGS is at -20 volts. I put a negative voltage between the gate and the source, or the gate and the, I should say the gate and the substrate, and that's not VGS, it's VG substrate. And I drive the electrons out of the floating gate. High voltage, likelihood of tunneling in the reverse direction gets to be much higher. When I want to program them, I do the exact opposite. I put a voltage between the gate and the substrate of +20 volts, and that drives the electrons into the floating gate. When I read them, I kind of go into this intermediate state where most of the rows are set for a voltage high enough to turn on all the transistors, and the row that I'm reading right here is in between the threshold voltages of the 2 volt threshold voltages I've set. Notice that this in between the 2 threshold voltages I've set is at 0 volts. That's saying that the floating gate transistor has an NMOS device has a negative threshold voltage. There are such creatures like this in the world. And we don't talk about them a lot because people don't use them as much as they once used to. But you may come across these terms when you're working in industry. When I say enhancement mode, I'm looking at an enhancement mode, mode, NMOS. All that term means is B threshold is positive. If I'm looking at something called a depletion mode, be really careful with these devices. They're not going to do what you expect. B threshold is a negative number. So it takes me actively putting voltage on the gate to turn these depletion mode devices off. When I was at Motorola, we were using, for our final stage power amplifier, it was 1 gigahertz, so normal MOSFETs didn't work. We used something called, and they were first of all made out of gallium arsenide. Second of all, they were MESFETs, not MOSFETs. So instead of being metal oxide semiconductor, it was metal epi-layer semiconductor, and they had better frequency response to them. So they could amplify at 1 gigahertz. The drawback to them is they were depletion mode devices. So if you did not actively put a negative voltage on the gate before the other voltages came up, you would actually, it would blow craters into these poor little devices. The way we fixed this, and this was horrible, it was a horrible argument that I got into, but I had to like I had to jump up and down, stop my feet for quite a while, is basically I got the audio logic guys to agree to power up my negative power supply first. So when you powered up the phone, that was the first voltage that came up. Then everything else lit up on the phone. They weren't happy with that, but they have to live with it. It was either that or blow up lots of MESFETs.
I don't know why they're unhappy.
They're unhappy because it's an extra work for them. Yeah. A lot of things in engineering are like that. You come up with a perfectly valid solution and nobody wants to implement it because they have to rewrite the manuals or something like that. So this is, remember when we build these NAND strings, I've got these transistors, they're in series, so the drain of one is the source of the other. So I can put them in very compactly into this device. I need to have contact to the P-well underneath this in order to be able, an individual contact for this string, in order to be able to drive those voltages, because I have to drive, to program and erase, I have to drive the substrate voltage. And I have to make the substrate voltage of this string different than the substrate voltage of the other strings, because I don't want to erase the whole device at the same time. Okay, so I need a separate contact for that. Is pretty much what's in that slide. This is a very pertinent slide to homework 5. I think this is the question that I thought didn't make any sense, so I just reworded it for you. And I left the nonsensical portion in there just because I was tired. And now I think it's just cute. So for homework 5, if we want to look at this device, and this is a voltage transfer curve for the floating gate transistor, there's 3 regions of operation here. Now this is what we're plotting here is voltage on the x-axis and current on the y-axis. So when the current 0, we're expecting this device to be in cutoff. When the current is large and stable, with voltage, we're expecting this to be in saturation. No, not in saturation. This is triode. I do this all the time. This is triode. And B, the slopey region where we could get analog operation is saturation. So when the string is on and I'm drawing current Well, first of all, when the string is off, how much current is being drawn? Anybody remember the cutoff current equation? We just did this at 280. It's 0. So this is 0 current. It's actually whatever the leakage current is. So it's nanoamps or picoamps or whatever. Up here, we're in triode. We're not in saturation. So if I want to calculate the current, I'm going to have to use the saturation current equation, which is on this slide. This is an amazing slide because it's like all the equations you need for one of the problems on homework 5. Now, if VDS is really small, VDS squared is going to be even smaller. You can neglect that term, and so this is what we mean for the ID and triode for a small VDS. The on resistance is defined as being VDS over ID. So if I took this equation here and solve for VDS over ID, I get 1 over K VGS minus VT. K in the Micheloni book is the same thing you're used to seeing in the Cedric Smith book as Kn. It's the transconductance parameter of the transistor. It isn't anything new. And if we want to find the saturation current, you can get it like this. That's not saturation region current, that is maximum current available. It's the number of strings minus 1 times the bit line voltage over R on. Okay, so that is, and that's just, and if you want to know the details of where that came from in more details, you can go back to the Micheloni book on Being Learn. Now, capacitors, we were going to start out with the idea of capacitive discharge. I'm discharging this capacitor and I'm generating a current. And this equation right here may look unfamiliar, but it comes from one of my favorites, I equals C dV dt. I changed the D's to delta because this is linear in the region that we're talking about. And I solve it for delta VC, and that's just going to be I over C delta T. Now, if I'm thinking about passive sign convention, this is a review, like all kinds of stuff, 188, 280. Passive sign convention says if I have a device like this, positive current goes into the positive terminal. Now for this capacitor, current is going this way. So current should be going out of the negative terminal. So this doesn't look like what it should be, but the positive terminal in this case is connected to ground for passive sign convention. So that will help you with all that, the following slides. The reason why the capacitor voltage is upside down. And I equals C dV dt. So when I want to sense what's coming off the NAND string, the first thing I'm going to do is I'm going to take this, and let's just change colors. Let's make it something really contrasting to black, orange. When we're in pre-charge here, we're orange. The switch is in this position, and the switch is probably implemented as a MOSFET. And whatever voltage is on here is going, this current is off, because I'm going to pre-charge before I turn the string on. So this current source is off, it's an open circuit. I pre-charge this capacitance up to whatever V pre-charge is. And this diagram down here shows the timing on the cell. I start out with the bit line at voltage 1, or it's at V bit line. The bit line's at VBL. And since I'm charging a capacitor, it's going to take time. Delta T would equal the change in voltage times C over I. It's amazing what you can do with one equation. So as this pre-charges, this voltage is going to go up. to after time, it's going to linearly go up. And after we get to time t0, it's charged to what our full level is. We have to go through and calculate the bit line capacitance to figure out how long we need to leave it charging to get to our desired voltage. And then we wait a little while, we just let this stabilize, turn everything off and let it stabilize. So my next move here in time is going to be, I haven't used that color. We're going to flip this back up into position 2. And this will be our evaluate phase. We've turned the floating gate transistors on or not in the string. And so if they're turned on, then my bit line, my NAND string is going to be drawing current. And that current, if it is on, will discharge the voltage stored in the capacitance of the bit line. Not a fixed capacitor, but it's like the C associated with that long poly line, that long poly capacitance. So if there's current flowing, what happens is after a period of time, this bit line capacitor starts to discharge. So we turn the string on or not, and if it's on, we're discharging. And then I can go wait some amount of time for the capacitance to discharge, called T evaluate, and then I can read the output. Because I know if this discharges, I have current flowing. I have turned that floating gate transistor successfully on. If it doesn't discharge, that means that transistor was off, and this voltage here is in theory going to stay up at whatever the pre-charge value is. So we pre-charge it and we either decay it with the capacitance or not. After T evaluate happens, I'm going to turn on this amplifier here. This is an open loop op amp. You can use a latch, an op amp, any variation on whatever you're using for the sense amp. You're going to compare the level that's on this voltage right here to V-sense. If it's above that level, I call it a device that is not turned on. Notice how I'm just avoiding saying the word 0 here. I get the polarity messed up, flash all the time. If the voltage is dropped down below V-sense, then I can call it the other flavor of my transistor has turned on. And if the transistor has turned on, it is a 1. Okay, I got that. I think I got that right. Okay. Sorry, I've been messing with the slides today. So what I've got here basically is this is in the place of the latch. This is probably a comparator or with a latch on it, or it's something that we saw in the DRAM chip where it's just a an N latch and a P latch or something like that. It depends upon how much sensitivity that you want to use at this particular time. But this is a block diagram basically of the whole system, just showing it as being a latch. Okay. Now we talked about program disturbs. Now let's say you are someone who stores your music on your flash drive and you play the same song over and over again for like a week. Yeah, that happens occasionally. There are people like that. What's going to happen? I'm reading the same word line many times without ever erasing it because I don't really want to erase this song. When I turn this word line on, no, this is the word line I'm turning on. This is my read level. This is my pass level. There could be small numbers of electrons that have enough energy to go into the floating gate. So I can actually maybe change one of these from being a low threshold voltage 1 into being a high threshold voltage 0 just by reading that same song too many times. There is an effect like this in DRAM. It's called row hammer, and hackers use this to basically disturb the rows adjacent to it. They turn on a row and leave that row turned on, which means you can't refresh it. And they write to it hundreds of thousands, millions of times. And so they're reading and writing from this row, and just that extra energy in the system is enough to possibly flip bits in adjacent rows. And
Yeah,
people,
I think Cambo talked about row hammer briefly at some point.
okay. This is why Micron gets upset when I tell him I want to turn refresh off. And I just smile and say it's for security. I can get away with stuff like that. They don't, yeah. They never buy it. Right. And this, the mechanism that they've named this for turning, basically turning on the other cells or putting enough energy in them to disturb them, is called silk, the stress-induced leakage currents, from having this string being read out too many times. It generates a positive threshold shift like we just talked about, and it may not, that transistor may not turn on when it should, and you may get errors. Now, the way to fix this is I just erase the whole block and reprogram it and start all over again. Okay, this is an algorithm we use a lot in the lab, even though we don't use Flash that much. Now, this is the idea here. If I want to program, I start out with a whole bunch of cells that are not programmed, they're erased. So they have a value of 1. And I want to turn some of them into cells that have a 0 on them. I could just have tried to apply the same voltage for the same amount of time to every single cell in the array and hope it works. But this is more reliable because the different devices actually need different voltages to program correctly. What I do is I kind of do this algorithmic loop. It's not a program. I measure, or it might be a program and test equipment. I measure the threshold voltage of the particular cell I want to program. And I set a voltage called V verify, and this V verify is my target voltage for the mean of the zeros, or maybe a little bit less. Maybe it's the lowest threshold voltage I can accept, because I'm expecting those threshold voltages to go up with time. So I set this V verify. If the threshold voltage is greater than whatever my minimum value, acceptable value is, I stop the program. Otherwise, I apply a slightly higher voltage to the word line. I measure the and then I measure the V threshold again, and I check and see if that one was good enough. And if it is, I stop. Otherwise, I just go on in a loop. You guys know about loops, they make you program. Okay, so here is the graph of what this looks like. Now this axis over here is the voltage that I'm putting on the gate, across the gate to the substrate. I start out at low voltages, and as I slowly step up the voltage, what I'm getting on the output is I'm getting my threshold voltage shift. If I'm looking for a threshold voltage of 1 volt, this would be when I stopped. It takes a long time, and this is part of the reason why Flash is takes so long to write to. Now, the reason why I want to do this is because I want a high level of accuracy in what the actual threshold shift is for each and every single one of these devices, especially when I go to, no, that's not yet here yet. Yeah, I don't, okay. Us, yeah, okay. Why do you write these like this? I have this whole storyline in my head, and then all of a sudden it gets shot because the slides are in the wrong order. Okay, so two different kinds of disturbs. Basically, I've got programming disturbs are going to happen along the same word line that I'm programming, because I'm putting the high voltage on every cell in that word line. Past disturbs from reading are going to happen along the NAND string direction, because I'm putting high voltages, actually higher voltages on the gates to turn these on. So I'm putting 20 volts on the one I'm programming. The other ones are at 10 volts. There are still some electrons that are going to be hot enough at 10 volts to go into the oxide, the floating gate, which is an oxide. Okay. Now, if I want to erase them, I select the block. This one says V erase is 23 volts. And then the last slide said it was 20 volts. I don't know exactly what they're using, but basically I put a high voltage. Remember what the last slide said. I put a high negative voltage across the gate to substrate. And that will allow me to erase it, drive the electrons out of the floated gate. And so I have to pay attention to what's going on in the other cells in that NAND string, because I will erase them eventually, so I don't have to worry so much this time. Okay. Part of the reason, and this is what I wanted to talk about a few slides ago, part of the reason why we go to this complicated process of stepping the voltage up for each individual cell and programming and verifying it is because when we go to these multi-level cells, when I'm trying to put 2 bits, 4 states in one cell, or when I go to 3 bits and I'm trying to put 8 states in there, or 4 bits, which is even worse, I got to put 16 states in one cell. I need a very high degree of accuracy for what that threshold voltage is. And I probably am going to program them on the low side, because as the read disturbs and programming disturbs go on with time, I'm going to increase all those threshold voltages a little bit. With the multi-level cells, what I'm going to get is a smaller array because I have more bits per floating gate transistor. But I need bigger periphery circuits. I need charge pumps for higher voltages. I need higher precision on the programming. I'm also going to have slower programming times, and it's going to increase the complexity of the algorithms that have to be implemented by the onboard microprocessor. And you thought this was just going to be reading zeros and ones. There's a whole world inside of here. Okay, so this is an MLC. In fact, this is a 2 bits per cell. So this is one way they found of implementing it. And you could play around with this and test different possibilities of what would work. But this is what they found worked for this particular technology. Is first of all, I start out with the erase cell. So I erase everything in the block. The ones I want to program into my first threshold voltage state, I program everything. D1 and D2 get programmed in the first round to this lower threshold voltage. Then I take the ones that I want to store D2 in and I add more electrons. And for some reason, they found that this process was probably too slow to do this a third round going from D2 to D3. So anything I want to program to D3, I'm just going to do directly. There was some kind of speed constraint probably involved in this. May or may not be true for the particular device you're working on. Again, it's like one of those engineering trade-offs. There's a million variables and you've got to figure out which one's the best for your application. And hope your change doesn't involve rewriting the manuals. That really happened to me when I was at Motorola.
That you had to rewrite a whole manual?
No. It was far worse than that. I had to deal with the kingdom of manuals. Basically, what happened is we were failing this one test when we were in development production. And I figured out why. It was because the algorithm we were using to measure the power output depended upon the fact that the IV characteristic of a diode is linear. So it tended to fail at low power levels when you're on the knee of the curve. And I just said, look, this is what's going on. And I was told, though, well, that's really, and then my first reaction, I was told, that's really interesting, but we'd have to rewrite all the manuals. Do you have any idea how expensive that would be? And so I gave them another option, which was basically we put more power into the power sensing circuit so we get it off the knee. Well, that kills our battery life. And finally, I got to be this big discussion with the senior staff engineers of me with the IV characteristic of a diode going, look, it's not linear. I don't know what happened. I left before. It was, yeah. There were so many manuals that had to be rewritten. It was a significant cost. It would had to go off to all the field service technicians and everything like that. And at the time, it wasn't just a PDF. It was a physical notebook binder with pages in it. It wasn't just upgrading your PDF. So yeah, maybe things are easier now. If I want to program a 4-level cell, I need much better accuracy. Each one of I need to control the width of that threshold, make sure there's no overlap in here. So generally what I do, and the program and the pass disturbs are going to increase the threshold voltage. So probably the best idea is to program and verify at the lower edge of what's acceptable and let all the disturbs later on shift some of those threshold voltages up. I need greater accuracy, which is going to mean I'm going to have to do smaller steps on my programming voltage. Each step takes a certain amount of time, so it's going to take me longer to program it. This is why these are used on lower end devices, where I don't care about speed and I don't care about durability as much. They're going to spend more time in programming too, and the programming time with the large voltages is what's going to wear them out. Yeah, I'm either way behind or you can just.
Tuesday, April 6th.
Oh, this is 2022.
Oh, we're way behind.
I'm either way behind.
It has been a really weird schedule.
It's a weird schedule. We had pseudo spring break, all this stuff, and we're actually should be a week ahead. But I've mapped it out. I think we'll get there in the right amount of time. So another thing with all these disturbs, sometimes I put too many electrons into the floating gate, I increase its threshold voltage, and when I read it, I get the wrong value out. So we have to have some kind of error correcting algorithm on these chips. They do this in DRAM also. We want the number of bit errors divided by the total number of bits is the probability that I get an error. Dr. Brower did that. The chip error probability is the number of chip errors divided by the total number of chips. And this is when I put the little IN subscript, that generally means like intrinsic. I got to go to a different color now. This is just bad. That will show up. When I put the intrinsic level is what the error rate would be if I had absolutely no error correction. And what we can see here is the no error correction is this solid line, and the chance of getting a bad read is a little less than 1%. Totally unacceptable. But if I error correct to a level where I can correct for 1-bit error, then the probability, it decreases greatly. What's this axis? Chip error probability, oh, page size. So as the page size increases, the probability I get an error also increases. So now I'm down, we compare for the same page size here that's like 1%. Oh, it's about the same. I don't get a lot of improvement. Wait, that's not good. But you can see that as I increase the number of error correcting bits, the probability that I'm getting an error gets much, much lower. Oh, that's why. So it goes from being non-readable, this is the error axis right here, to maybe like 10 to the 8, 10 to the minus 6. I get much better results. 1 part per million is usually what they're shooting for. That's a probability of 10 to the minus 6 that I have a read error. So error correction has to be done in order to make these chips functional.
It means that you're using extra transistors in memory, right?
Yes. Every time you have to correct for more bits, you get to do this over and 5. Every time you have to, like if I have to correct for 1-bit error, it takes, I'm going to need X amount of memory to generate a Hamming code that can correct for whatever errors I have in there. If I want to correct for 2 errors, I have to have a longer wasted memory that I'm just using for error correction. So in theory, I think it comes out to be like, but on the homework problem, it comes out to be about the point where the number of error correcting bits you need is about as big as the number of data bits. You've effectively cut your memory in half, but it's much more reliable. And who wants a memory that doesn't remember things correctly?
I mean, at that point, couldn't we just save everything twice?
Yeah,
And
they
not have to do all the error correcting stuff?
well, they do that too. If you get into satellite work, they do the thing where they have redundant memories and they save everything twice, and they do error correcting.
Great.
Because memories in space is a whole another thing. It's bad. This is another slide you're going to need for homework 5. This is again from the Micheloni book in chapter 7. I highly recommend getting out that page of the book on the PDF and looking at this when you're doing this homework problem. You have to get straight what these variables are. When I say 2048 data bits, that's like 2 to the 11th. So that's 11 bits of data, basically. And what is it going to take to correct for that? Get out the book, read it. And use MATLAB, because the way I solved this problem, it's a summation. The way I solved this problem is I generated some MATLAB code that basically calculated both the left side of the equation and the right side of the equation for me, and I found out when this was true. It saved me a lot of sanity, because trying to do this by hand is not easy. I probably should have just done it in Excel. I've done that too.
I don't use MATLAB ever.
Yeah, Excel would probably work. This was back in the days when I thought I had to program, and I didn't. Just realize that I do know how to program, but my only language is Excel. Fallon is at Gore now, and that was one of the things that really got to her when she first started working there, is there are people there at Gore who swear that that's their programming language is Excel. I wrote this program in Excel, and she's just like, no, 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 no. There's some geezers around like me that do think stuff, refuse to program. Now, one of the things that is kind of hitting really hard on flash right now, even at 30 nanometers, that only means you have a few hundred electrons to differentiate between the different levels. The accuracy is getting way worse. Going down to smaller processes means I have fewer electrons. So there's a limit to how far this technology will scale. The floating gate limitations. One of the ways they're getting over that, and they've pushed NAND over this hump and got still greater densities out of it, even using a 30 nanometer node, is to do this 3D stacking. Take one silicon array of NAND flash, stack it on top of another array, have through silicon vias on this part of the device, and then this layer is basically kind of like almost like a silicon printed circuit board that's making sure that these through silicon vias actually connect together. And then they can run the bit line or the word line vertically through the array. And so effectively address a larger number of strings at the same time. Now this charge trapping memory, basically, nobody's pursuing this anymore. I'll just tell you what traps are. When you have any semiconductor crystal, you've got a conduction band and you have a valence band. Now, this may be ultra pure silicon with maybe only like 1 part per billion of impurities or something like that in there. But there is that 1 part per billion. And this 1 part per billion happens to be an atom that has an allowed energy state somewhere in this band gap. This is called a trap. And this is the reason why ReRAM conducts current, even though it's a capacitor, when it's pristine. Now, if somehow I get an electron in this trap, it can stay there. Some of these traps have decay rates of like seconds. Some of them, what?
That's not bad. Like multiple seconds?
Multiple seconds.
Compared to the microseconds that ReRAM does?
Yeah. Some of them have traps in the microseconds. It just depends upon what material it is, what conditions it's conducting under. So basically, you have to treat that electron in that trap like it's a random process, because you don't know when it's going to go off. So these things suddenly get enough energy to get out of the trap and go someplace else. It's going to create some noise. So all these impurities create noise, and we actually use traps. Traps are, we'll talk about it when we get to ReRAM. These aren't really being used very much. This is an older new emerging technology. ReRAM and MRAM are actually in production. So it's a little bit better than emerging. They're just lower densities than NAND flash. You can get a 1 terabyte NAND flash in a really small package. You can, and when I talk about density, you can get 16 megs of MRAM in a small package. So they just don't have the density of other devices. When it gets to that, when it gets to the point where it starts competing with NAND flash and the prices go down, we'll have the one memory to rule them all. This isn't really important. This is more important. We're gonna get out early today. So when I'm dealing with this 3D structure, remember these are separate wafers here. So this is like silicon wafer 1, this is like silicon wafer 2. I put the through silicon vias coming down through there and some kind of interposer that makes sure that they all get connected together. I can put drain contacts, I can put bit strings going down, I can put word lines going down. And then this 3D NAND becomes just a bigger NAND flash. And this is how they're dealing with the density problems. No, I did put that in there. There's a reason why. I didn't make this slide, honestly. And I can't change the font on it.
I'm okay with Comic Sans.
But,
I'm okay with Comic Sans.
okay.
What do you not like Comic Sans for?
My son's capstone project, he went to NAU. He already had a geology degree. So he went to NAU and got a geography degree. Okay, so he's in the School of Social and Behavioral Sciences with geography. His capstone project was that he was up at USGS mapping a canyon on Mars that had never been mapped before. Decent capstone project. There's somebody else in his department, and he had in his college, and he had to sit through the presentations. Their entire capstone project was don't use Comic Sans font.
That's
That's an interesting project.
pretty good.
You know, here's Ian with this. This is my canyon. And then there's the other version. You know, Ian has a job. So what we're doing here with this slide, and I'm running out of slides. Yay, you can go home early. VFG is the floating gate to ground. So there's the floating gate. That's the voltage here we're referring to. The substrate is tied to 0 volts. Everything is capacitively coupled. There are 4 capacitors in here. There is CFC, is between the control and the floating gate, between the floating gate and the source, between the floating gate and the body, and between the floating gate and the drain. So we have 4 capacitors on there. And we want to find out, we're going to apply charge conservation to this and find out what voltage it takes to get there. My Q equals CV. My total of the CVs are this floating gate capacitance times the voltage across it, the floating gate voltage minus the control gate voltage, et cetera, et cetera, et cetera. And I go through and I write all those separate charges down. And then we define the total voltage has to equal the rest of this. And we do some algebra here. We get CFC time, yeah, okay. And then yeah, okay. That's how you model. You won't see that one on the homework. I usually just skip that slide because it's in Comic Sans and it makes me. So this is the model of a floating gate transistor as P-SPICE sees it. There's a lot of effects it's taking into account. What? I am probably the only person at this school who's ever done this before. It's kind of an unusual thing to have to happen to you. But I have had to take one of these models and adjust every parameter in it for temperature. Not just in a normal temperature range that like P-SPICE will actually take care of, but I had to take this T-nom, which is 27 degrees C, and take it down to minus 230 degrees C, 35 Kelvin.
Really low.
Yeah, and that's where SPICE's model just completely falls apart. So I had to do this because we were actually spending $1 million to build a new chip, and we had to know what it was going to be, and we were changing the unit cell. It was like it was a imager, and imagers act like DRAM memories. They use kind of an old school instead of using the 1T 1C, they use kind of an old school 3T 1 photodiode cell, and we changed it from the standard configuration into a 4 T cell, and to get more electrons out. We got like 100 more electrons. It was a big deal. Okay. The astronomers could stare at things for like the whole 20 minutes longer before they would hit saturation. So that was the whole thing, is in order to verify that what we were doing worked, I had to get the transistor model right at our operating transistors, at our operating temperature. Not only did I have to just fudge it, well, you can't fudge something like this because you don't know what you're doing. I had to go through and theoretically figure out what each one of these were, how it was affected by temperature, get an estimate of it, show the model in PSpice, and then take other transistors down to 35 Kelvin and verify their actual results matched my theoretical results. That was a pain. He was a pain to work for, but this is why he got such good results. It's because we did stuff like that, and I don't want it. That's irrelevant. I'm done. Any questions about life, the universe, or the homework?
I was going to ask a question about just as a reference to Monty Python, but I decided not to.
Perfect. Let's see who is here. Let me do that really quick. I'm just going to stop sharing. That's the easiest way to do it, is so I can see everybody at once. I can see everyone's black square at once. Hamad is still not here. He dropped. He was having computer issues. He couldn't do the projects. He dropped. This is a really, it's a really old copy of my thing. Nolan's not even on here yet. And he dropped. So the only people who are not here are Hamad and Chujian, who watches the videos, because right now it's like 2 o'clock in the morning in China. So any questions on the homework? Because I've been getting several questions in office hours.
I might come in tomorrow to ask for questions on homework.
Okay, that works too. Some people may not have looked at it yet. It's over the semiconductor physics slides. So you can go back and review those. It's what I consider to be basic stuff. So I know you haven't gotten a lot of it yet, but that's useful. Can I give you any hints? I just need to know what your questions are. Oh, one thing that most people, the question I get the most is on 2C and D. And my actual homework says Q phi m if the gate is aluminum. And there's in parentheses, it says you need to look this up. Q phi m is a material property of aluminum. So if you look up work function of aluminum, if you Google that, Wikipedia even has a page on work functions of metals. That should be fairly easy to find. Q phi m for poly is a lot harder to find. I'll give you that one now. Again, it's a material property of poly, and that took a little bit more digging when I was looking for it. That is 4.05 electron volts. And my solution says given. So I know how long it took me to find it.
Can you say that again? It's 4.05.
Electron volts, yes.
Okay.
The answer to 2D.
Yeah, I like the layout things a lot more better than the semiconductor physics.
Yeah.
I'm not a physics person, apparently.
The layout, you know, that's stuff that, you know, like people like TSMC do too, because they get the designs from companies, but there's got to be somebody there that checks them against their design rules to see if they're violating it. And there's also somebody there, and because that actually happens, there's also got to be somebody there to do layout test structures. And so when you run a wafer through, you're going to want to put test transistors periodically through on the wafer so you can test your process and make sure that if your customer comes back and then you actually write the data sheets out for that and you send it back to the customer with the devices saying this is the KN, this is the COX that we measured on this given particular day. So there's people who've got to lay those things out for the different things and all that.
They can hire people like you to do that.
Oh, thanks, Julie. I'm gonna go
Okay.
back and lay down again.
Okay, have fun.
Yeah, the
It'll go away soon.
Yeah, it's kind of wrecking me a little bit.
Okay. I'm gonna stop.